Hello and welcome to the Chemistry Academy. So this video is going over the second half of section 2 of the 2029 National 5 chemistry paper. If you're looking for help with questions 1 to 6, you'll find that in a separate video as well as the multiple choice in a separate third video. Just don't like to make these ones too long. So this one will cover questions 7 to the end of the paper. So if we get started, 7a, state what's meant by the term homologous series. Now this is a definition that you need to know word for word, and ideally you would refer to it as a group of molecules with the same general formula and similar chemical properties. This definition often gets confused with isomers, which are molecules with the same molecular formula but a different structure. So just remember, for homologous series, you're looking for the group of molecules that have the same general formula and similar chemical properties. Okay. Definitions are good things to put on flashcards. If you put the term on one side and then the definition on the other, and then you can play a little revision game with yourself. It's all very fun. So then an exam to name the homologous series that this hydrocarbon here belongs to. So we'd want to see which general formula it fits. So the general formulas we know are CnH2n and then also CnH2n plus 2. Now this one here fits 2n plus 2 because if we take the number of carbons times it by 2, that gives us 50. So to get to 52, we would have to add 2. That means that because it fits this general formula, it must be an alkane, because the general formula for the alkanes is CnH2n plus 2. If it was C25H50, then it would fit CnH2n, and that means it would either be a member of the alkenes or the cycloalkanes. So you would need more information than just the general formula to be able to work out which one of those two it would be from. And then part 2, you were asked to write the molecular formula for the molecule that had 72 hydrogens from the same homologous series. So this one's a bit tricky because you have to kind of use the molecular formula the general formula, backwards from what we would normally do. So we've got the number of hydrogens, so we can write H72. We need to work out the number of carbons. So normally when we do it the other way around, we times by 2 and then add 2, but because we're doing it backwards, we need to take away 2 and then divide by 2. So if we take away 2, that would give us 70, and then 70 divided by 2 would give us the 35. So that would be the molecular formula for the molecule we're looking for. A predicting question for these ones, the best thing to do is look at what the change is each row you go down in the table. So you just really need to take these numbers away from each other. So you can see here it goes up by 13. It's good to identify if it's going up or down. Then it goes up by 13 again, and then it goes up by 12 this time. So to predict what it would be if there was 24 carbons, that says going up one more time. So you can either add on 12 again, or you could add on 11, potentially add on 13. You usually get a range for these ones. So if we were to add on 12, that would give us 393. For this, you can actually have any number between 391 and 394. So that's what I mean, you kind of get a range for these ones. But the best thing to do, if ever in doubt, is always just add on the last difference that you see in the pattern. Also, you don't need to put, I should have said here, that is degrees Celsius, but you don't need to put the units because they are in the question. If you are going to put them, just double check that you're putting the right units. So then a literacy question. You're to read the passage to work out or to state where beryllium is formed. So if you read through the passage, you should find that it's formed in supernova explosions. So you would just copy that down. You don't need to put it in your own words or anything for these questions. Okay. Then for the elements found in the mineral beryl, so we'd want to find what it says about beryl. So here's the mineral beryl here, and it gives us the chemical name. So we can see its chemical name is beryllium aluminium silicate. So we can work out the elements in it from its name. Because it's got beryllium in its name, it would have beryllium. Because it's got aluminium in its name, it would have aluminium. Because it's got silicate, silicate would be silicon and oxygen. Okay, so you've got beryllium atoms, aluminium atoms, silicon atoms, and oxygen atoms. If you were writing it in a formula, oxygen would have to be written as O2, but because you're just stating it as a element that's present in a compound, you don't need to write it as being diatomic. But if you did, that's also fine, you wouldn't be penalised. You could write the names of these as well, but I just didn't write them for the sake of time, because you guys don't want to really be sitting here watching me write out words. So then, question C, write an equation using symbols and formulae to show the reaction taking place when beryllium is extracted from beryllium chloride. So there should again be information in the passage about that. So if we look here, it mentions beryllium being extracted from beryllium chloride, and it says it's by reacting the compound with potassium, and then potassium chloride was also produced. So it's a good idea to identify what are the products, what are the reactants. So I'll put the products in green. So the beryllium's extracted, so that's a product, and then it tells you the potassium chloride is produced, so that's a product too. The reactants I'll put in pink. So the beryllium chloride is the reactant because that's where you're extracting the beryllium from, and you also then react the compound with potassium. So our pink ones are our reactants, so it already gives you the formula for beryllium chloride, very helpful. So BeCl2 plus potassium, which the symbol for that is just K. Remember to just double check in the periodic table if you're not 100% sure. And then you're producing beryllium, which is Be, and then also potassium chloride. So that would be a K and a Cl. And what we just need to double check is that what their valencies are. So if we go to the data booklet, look at the periodic table, potassium's in group 1, so that's got a valency of 1. Chlorine's in group 7, so it's also got a valency of 1. So that would just stay as a 1-to-1 ratio. So we don't need to add any more atoms or change the formula at all. And that would be us. You don't need to balance it or anything, like they said. Symbols are, these are the symbols. The formula is showing how many number of each atom is in the compound. You don't need to put state symbols or anything. Then for D, the type of reaction when you're extracting beryllium from the beryllium chloride. So beryllium ions are changing to beryllium atoms. Now beryllium is a positive ion because it's a metal, and it'd be Be2+. We can work that out because we can see there's 2 chlorines attached to it. Each chloride ion has a 1 negative charge. I can draw the ionic formula on here. So if that's 2 negatives, then this beryllium has to be 2 positive to balance that out. So the beryllium ions are 2 positive, they then become neutral beryllium atoms. That means it's gained electrons, so they've gained negative electrons to become neutral, so that would be reduction. So remember, oil rig, oxidation is lost, reduction is gain. As a rule of thumb though, you can just memorise that anytime you're extracting a metal from a compound, it's going to be a reduction reaction that's happening to the metal, okay? Because metal ions are always positive, so if you're extracting them and forming the neutral atoms, then they're always going to be gaining electrons. For E, you're asked to write the nuclide notation for a subatomic particle discovered by James Chadwick. So if we go back to the passage, again, we're looking for what the subatomic particle might be, and we can see that James Chadwick called his new particle a neutron. So hopefully from the nuclear chemistry topic, you can remember the nuclide notation for a neutron. It's just N with a mass of 1 and atomic number of 0, and there's no charge on it at all. Okay. So then question 9, the term used to describe all chemical reactions that release heat energy would be exothermic. Remember, the reactions that consume heat energy from the surroundings are endothermic. So again, that's maybe other things you want to get on a flashcard. Exothermic is a chemical reaction that releases heat. If you think of exo like exit, thermic like heat, it's like exiting heat. So heat's exiting the reaction. And endothermic is where the heat's been taken in. So then for the energy from fuels calculation here, everyone usually likes these. One thing to watch out for though is they like to give you the mass of the fuel. You don't need that until you do higher chemistry. So if they give you the mass of the fuel, just ignore that. You only ever care about the mass of the water, which is actually what you're trying to calculate in this particular experiment. So sometimes when you read these, they do seem a bit confusing. So the best thing to do is if you see them mentioning energy, you're going to use EH equals Cm delta T. So if you write the variables down the side as a wee list, and then you can pull the numbers out that you've got. So it's given you an energy here of 8.36 kilojoules. It's also then given us a temperature change of 40 degrees Celsius. It's wanting us to work out the mass of water in kilograms. And that's all the information it gives us, but C we can always get from the data booklet, and it is 4.18 kilojoules per kilogram per degree Celsius. I always like to write the units of specific heat capacity because it reminds me about the mass being in kilograms. So quite often you have to convert the mass of water into kilograms because it'll have given it to you in centimetres cubed. So to do that you just divide by 1,000, but just don't forget to convert your mass. So now we can see that we're trying to work out the mass. We're going to use EH equals Cm delta T though, so if we write the equation out, but then we're going to need to rearrange it. So it's up to you if you want to rearrange it after you put the numbers in or before you put the numbers in. I guess it depends how confident you are at maths, but I quite like to put the numbers in first and then rearrange it. So that's all my numbers in. So we want M on its own, which means we need to divide by the 4.18 because it's times on this side, it'll be divided on the other side. And then because this 40 is times on this side, it'll also be divided on the other side. So 8.36 divided by 4.18, and it's also divided by 40. And that should give us M. So if we put that in our calculator, that should give us, just put it in quickly, 8.36 divided by, and I would probably put brackets around this if you're putting it in your calculator. So if you've not got the right answer for this, that just might have been what the problem was. And that should give you 0.05. And that is in kilograms because our specific heat capacity was per kilogram. Okay, so quite straightforward once you got your numbers in. Then these questions about this experiment are quite common. The reasons for the improvement. So if you use a copper can, that is a better conductor of heat than glass is, because it was glass beaker that you used before. So you just need to say better conductor. Copper is a better conductor of heat, sorry. Would be better to more explicit. It's always important to be very clear in your answers and try not to leave any room for confusion. So make sure you name everything you're referring to. And then the heat shield, it prevents loss to the surroundings. It prevents heat loss to the surroundings. It's important that you say it's to the surroundings. Sometimes at National 5 they'll accept it without it, but when you move up to higher it's very important. So it's just a good habit to get into now. Okay, so it prevents heat loss to the surroundings. They need to give me bigger boxes. So then for this question here, it's a problem-solving question where you're asked to write a general statement linking the position of a functional group in the alcohol to the type of the product formed. So you can see the type of product is in the middle. So we can see there's two types of products, aldehydes and ketones. So we want to look at what the difference is in terms of where the functional group in the alcohol is. So if the functional, for the two that ended up as aldehydes, the hydroxyl group or the functional group was on the end carbon, whereas when it was a ketone, the functional group was on middle carbons. So in terms of writing a general statement, you just have to really either say that if the functional group or the hydroxyl group is at the end of the carbon chain, an aldehyde would be produced, or you could say if the functional group is in the middle of the carbon chain, then a ketone is produced. So you can say either way round, it doesn't really matter. I'm just going to go with the end of the chain one. So if the hydroxyl group is at the end of the chain, an aldehyde will be formed. Sorry. Perfect. So then 9C part 2, the following alcohol reacts with hot copper 2 oxide to produce an aldehyde. Draw the full structural formula for the aldehyde produced when this alcohol reacts with hot copper 2 oxide. So we want to look at the examples that we had here and see how the alcohols look different when they become aldehydes. So it's like a game of spot the difference. So if we have a look at what's happened here, and you just want to think in basic terms, does it look different? So you could say that it's lost an H and the OH has become a double bond O instead, and that's the same for this one here. So that's basically what we need to do to this molecule. So we need to take that H away, and that then becomes a double bond O. So that would be the aldehyde that ends up forming. So we just draw that like that. Okay. Sometimes it's helpful for these questions as well to kind of spot the different ones. If you write down what the differences is, like if you were writing down steps to give to your friend, to imagine they had this molecule and you were trying to get them to change it into this one, like what simple steps would you give them, and note down those steps. That often helps you then have steps to follow when you go on to do the question, like in the example you're given. Makes it a little less complicated. So then apparatus X is either an ion bridge or a salt bridge. You can call it either. I usually call it an ion bridge, but like I say, you can call it a salt bridge. You just need to remember that that's what that piece of apparatus is called. Then for drawing an arrow to show the path and direction of electron flow. So we don't have metal electrodes here, so we can't, looking at the electrochemical series isn't really very helpful, as helpful in this one. But they do give us the reaction, so we can actually see which one's gaining electrons and which one's losing electrons. So in beaker B, the electrons are being produced, so that means they're giving away the electrons. And in beaker A, the electrons are being picked up, they're being reacted with, so they're being taken. That means the electrons must be going from beaker B to beaker A, and hopefully you remember that the electrons always go through the wires. So we basically just need to draw arrows on the wires going in the direction from beaker B to beaker A. If you study physics, you might know that it wouldn't necessarily travel through a voltmeter because the resistance is too high, but people who write chemistry exams don't seem to know that. So sorry for those of you that are really into physics and get upset every time you see this diagram. I used to work with a physics teacher that would not enjoy seeing these chemistry questions ever. So I would always hide them from him in the staff room if I was ever marking at lunchtime. So then name the type of chemical reaction taking place in beaker B. So we've kind of already half answered this because we can see that the electrons are being given away. So that means the electrons are being lost. Remember oil rig, oxidation is loss, reduction is gain. So because the electrons are being lost, it will be oxidation. Okay. So then the redox equation for the overall reaction. So what we have to do here is make sure that the electrons cancel out. Let's rub this out. So we need to times the top one by 2 because we've got 2 electrons here, but only 1 electron here. So if we multiply the top one completely through by 2, then that allows those electrons to cancel. And then everything we're left with just gets written on the same line. So we have 2Fe3+. Also, if you struggle to see which is on what side of the arrow, then you can build a wall. It sometimes helps to see what stays on what half of the reaction. So you've got 2Fe3 plus 2I minus going to the 2Fe2 plus the I2, and that was a liquid. You don't need to put the state symbols, but if they're there you might as well just copy them down. And then carbon in the form of graphite is a suitable material to use as an electrode as it does not react with the solutions. The other reason it's suitable is because it can conduct electricity. So carbon graphite is the only covalent molecular or covalent network structure that can conduct electricity, and that's because it has electrons that are free to move. So that's something to remember for your properties of bonding, structure and bonding stuff as well, is that carbon graphite is a covalent network, but it has electrons that are free to move, so it can conduct electricity. So then question 11, I've not got too many questions to go now, don't think. So this formula for calcium carbonate, so you want to do your SVSDF and you're asked to show the charge on each ion, so that it's technically the ionic formula here. So the symbol for calcium is Ca. The carbonate you will find on page 8 of the data booklet. So if we go to page 8, you'll find carbonate here. Because it's got a 2 negative charge, that means its valency is 2. So CO3 2 minus. Calcium's valency, if we look up the periodic table, it's in group 2, so its valency will be 2. Remember the valency pattern goes 1, 2, 3, 4, 3, 2, 1, 0. It's useful to write that in your data booklet if it's not something you're comfortable with yet. So the valency of that's 2, the valency of this is 2. We swap them over, it becomes 2 and 2. That we can simplify then to 1 and 1, which means our formula is going to be CaCO3. Because they want the charge of each ion, we put the 2 minus on the carbonate. A calcium's charge is always 2 positive because it's in group 2, so we put a 2 positive on there. And that's it. The acid you would use to prepare calcium propanoate, so that is a salt. Because it ends in propanoate, it means you've used propanoic acid. Learning the salt name endings is something you'll want to make sure you know, so you can go and check out my video on acids and bases for that, or neutralization, one of the two, and there should be naming salts in there. So propanoate means you've used propanoic acid. And then for the finishing off with instruction 3, if you're adding a carbonate for a neutralization, which is what this is because you're preparing a salt, carbonate is useful because it will fizz, so carbon dioxide will be produced when the carbonate reacts, so you'll know that your reaction is finished or you don't need to add any more calcium carbonate if the substance stops fizzing. So all you would really have to stay here is continue adding the calcium carbonate until there is no more fizzing. Or you can call it bubbling or effervescence or whatever. But it's because no more CO2 is produced. Okay, that means you've then fully reacted it. Then once that happens, you then, to get a dry sample of your salts, once you've got your neutral solution, which is what you'll have here once you've added enough calcium carbonate to stop it fizzing, you then have to filter off the excess calcium carbonate that you've added, because there'll be bits of calcium carbonate floating in there that haven't reacted. So you first of all do filtration, and that removes the excess calcium carbonate solid. And then to get your dry sample of your salt, you then have to use evaporation to get rid of the water, because your salt will be soluble. Okay, if you're ever asked for 2 techniques in an experiment, it usually is filtration followed by evaporation. So if ever in doubt and you've been asked for 2 things, just go with those 2. So then the term given to a solution of accurately known concentration, that is a standard solution. Again, that's another definition you want to get on a flashcard, ideally if you're taking higher as well, because they ask about standard solutions a lot higher, and actually even also advanced higher. So yeah, standard solution, a solution of accurately known concentration. Then a wee calculation here. So you're asked to calculate the mass in grams of sodium carbonate required to prepare 200 centimetre cubed of 1 mole per litre solution. So if we write down the numbers we've got a volume, 200 centimetres cubed. We've got a concentration. We can tell that's a concentration because it's moles per litre. Don't get confused and think that's number of moles. If it's got a per litre after it means it's a concentration. And we're trying to work out a mass. So I always like to put in what my question mark is. And it's a mass of sodium carbonate. So we have volume and concentration. How do we get to a mass? Well, the one thing that links those two things is a number of moles, because we've got the NM-GFM relationship and we also have NV-C relationship. So we start off by working out the number of moles first of all, so that's C times V. Just don't forget to change your volume into litres, so divide it by 1,000, so that'd be 1 times 0.2. Not very difficult maths that, so that's quite easy. Oh, and here's me putting in an extra 0. Okay, the GFM of sodium carbonate we can work out from the data booklet. So we go to our big table. The GFM of sodium is 23, carbon is 12, and oxygen is, I know it's 16, but I'll just find it for you anyway. So we've got 2 times 23, 1 times 12, and 3 times 16. So if we add that all up, we should get 106. So then to work out the mass, that's N times GFM. So that'd be 0.2 times 106, which if we put that in our calculator, 0.2 times 106, that gives us 21.2 grams. You could round that to 21 grams if you wanted to, that's no problem, just as long as your rounding is correct. So then to improve this titration, there's a few things that the student could do. They could move the burette so that they're taking the reading at eye level. They could reduce this distance between the tip of the burette and the conical flask, because that's, you could get some splatter and solution loss there, so it's not very accurate. They could also use a white tile or a white piece of paper underneath. That helps see the colour change more clearly. And they could always also move the clamp of the burette a bit more into the, the clamp of the clamp stand more into the middle of the burette, but that's more of like a stability thing. But ideally for just improving the technique, moving it lower would be the biggest improvement here. So move the burette down to take reading at eye level. But like I said, you could have had all of those other things as well. And if you're asked to explain why you need an indicator, you just need to show the end point. Try to avoid saying to give a colour change. They don't really accept that. Although it does give a colour change, they want you to know, they want to make sure that you know that that then means that a reaction has been completed, so that the reaction is ended. So the better phrase to use is to show the end point rather than to give a colour change. Okay. And then results that are within 0.2 centimetres cubed of each other are known as concordant. That's another word you need to know the definition of. So again, maybe something to get on a flashcard. Concordant results are always within 0.2 centimetres cubed of each other. Then we've got our titration calculation. So we're trying to work out the concentration of hydrochloric acid. So that's this one here. And if we go back to the picture, we can see we've got information on sodium carbonate. We've got a concentration. So that means that'll be our other chemical that we're using. So the concentration was 1.0 moles per litre. We've also, in this question here, so sometimes not every bit of information needs in the picture, we've got a volume of sodium carbonate, it's 15 centimetres cubed. And then in the picture, if we go back to the picture, we've also got a volume of hydrochloric acid, which is 20 centimetres cubed. So now we can see that's the two chemicals we're using for the calculation. So we can rewrite their formulas. And then the mole ratio is 1 to 2. Because it's concentrations and volumes for both of them, we'll list NCV underneath both. And we're trying to work out the concentration of this one, and we have concentration of this one. We've also got the volume, which remember we need to turn into litres, so I'll just put it into litres now. And then the volume of the hydrochloric acid also needs to go into litres. So then you can hopefully see, that you can work out the number of moles of sodium sodium carbonate, sorry. So N equals C, N equals C times V. So we've got 1 times 0.015, which again, hard maths, gives us 0.015. Now we can move across. We're going from 1 to 2, so we need to times by 2. So that would give us 0.03. And then C is equal to N over V. So we would have 0.03 over 0.02, which would give us 1.5. And that will be in moles per litre. So again, you don't need to write the units, but if you do, they need to be correct. So you can always check to see what they should be in the question. Then question 13, this is our last question, this whole paper. Open-ended question, so basically asking you to explain why the attraction of positive and negative charges is important in chemistry. So you want to think of all of the occasions that you've seen positives and negatives attracted to each other. So that means you could talk about the structure of the atom, because that's got positive protons in the nucleus and negative electrons that circle around the outside. If they didn't have opposite charges, the electrons wouldn't orbit around the nucleus. So you can draw a wee diagram, a structure of the atom, give an example of atoms, talk about atomic number, etc. We've also got ionic bonding, where you've got oppositely charged ions held by electrostatic attraction. You've also got metallic bonding, which is where you've got the positive ions surrounded by delocalized negative electrons. In covalent bonding, it's also important as well, because the two positive nuclei have a mutual attraction for the shared pair of negative electrons in the middle. So that's what holds the atoms together in a bond. You've then also got electrolysis that you could talk about, because electrolysis uses splitting, uses oppositely charged electrodes in order to split a compound up. So for example, you could electrolyse sodium chloride solution, and what would happen is your sodium ions would go to the negative electrode and your chloride ions would go to a positive electrode, and then you would end up producing just sodium metal, and then chlorine gas. So there's lots of different things here. You're basically just looking for anything you can think of that you've learned about that has charges on it. Okay, so I hope you found, the other thing I should probably said again with the open-ended questions, try and pick two or three things that you can go into a lot of detail with, and I mean like full paragraph and diagrams on each, or pick like 5 to 6 things that you can maybe write a few sentences on. That's the best way to try and maximise the chances of you getting 3 marks in those. So I hope you found this video useful. I hope your revision is going well. If you did find this video useful, please give it a like. Don't forget to subscribe, and I will see you again soon.